Hello, and welcome to lesson number 15, the iterative design process. So basically what we're going to be covering is a synthesis of a couple of the previous lessons of basically estimating and calculating your overall score. So what you've already done up to this point is you've gotten your efficiency, you've gotten your economy, so now we basically sum those together to get our overall score. And I've just constructed a very simple spreadsheet here where I pretty much have some of my main data or model parameters just to characterize that particular bridge. And I have here just kind of the example design that we've worked on in our previous lessons. So here it is. And basically what we're going to try to do is optimize this, or kind of decrease this overall score, just by making a few changes and then just observing how this overall score changes. So the first thing that I'm going to try to do is I'm going to go to SAP, and how do we know what's a good place to start? Well, here's one way. Go ahead and run your analysis, and once it runs, go up to Show Energy and Virtual Work Diagrams. So first of all, select your forces as whichever particular case and step you're interested in, and just for example, I'll do case 3, step 2. So for both of these, make sure that these are the same, because that way, essentially, you're defining actual energy, and energy only has physical meaning if the forces and displacements that you're multiplying together come from the same loading. If you're doing different forces multiplied with different displacements, then it's no longer energy, but it is some kind of virtual work. But for now, just make sure these are the same. I'm going to just, for demonstration purposes, go relative and not show the values, but more or less what we're looking at is a visual representation of the stored elastic strain energy in each of these members. And you can kind of see in the spectrum going relatively from 0 to 100. It's pretty much just kind of saying, okay, well, if you're down here, then you're not having that much relative energy stored in you. But if you have a high, color, then you're pretty much really in danger here. You're having a lot of proportional energy stored in that member, which is not good. You want to kind of make sure that your energy is reasonably well distributed throughout the bridge. So how do you go about resolving that issue? Well, you can pretty much just kind of say, well, okay, these higher colored members, I'm going to just change to maybe a larger tubing size. So for example, I'm going to select, these green ones and maybe these blue ones on both sides of the bridge. And note that you would also have to do that for the case of these members on this side of the bridge. So that basically means that, even though we're maybe measuring loads from this side of the bridge, there's the potential, based on the rules, that you could also be measuring loads from this side of the bridge. I've only defined it for measurement from this side, but you have to do it from this side as well. So I'm just going to symmetrize everything that I select. So to actually select things, just go ahead and unlock your model, and I'm going to hopefully be able to select these. So these ones, right? These ones. And same thing, symmetrize it on both sides of the bridge. Those ones. Kind of rotate your model just so you can get a better view. I'm going to rotate it around this way and select the members on the other side. Alright. So yeah, there's probably better ways to go about selecting this, but I don't know. This is good for just a quick example. So now I have all those members selected. How do I know what they originally were, at least in terms of section sizes? Well, I'm just going to use extrude view to kind of give it a little demonstration. You can see they're actually, the 3/16 inch diameter tubing, which is really small, especially considering how much energy they're carrying. So what I'm going to do is I'm going to go up to Assign Frame Sections, or Alt-AFS, and I'm going to bump these up to maybe 1/2 inch diameter tubings with 0.35 wall thickness. So now you can see these have all been bumped up, and I'm going to go ahead and run this model now. But before I do that, I'm going to save this as a new model. So instead of version 0.0 or 1.0.0, I'm now going to bump it up to the next iteration of that. Save it, go ahead and run your model. Woohoo! Now I'm going to just go ahead and output all my data into Excel tables, because that's how I'm going to process it. So make sure you have your joint displacements and your base reactions being put out. You get them. put these export all tables to Excel. Alright, and I'm just going to go ahead and copy these right into the existing spreadsheets that I already have. So notice in my spreadsheet I'm actually referencing a lot of data from my previous economy data tab and my auto efficiency scoring. So in order to do this, I can just kind of copy these values back into these tables that I have here, and it'll automatically calculate my efficiency score. But note that these are all linked pretty much. This is actually taking data from my economy and my efficiency scoring tables. So if I change these, then it's going to change basically this. And I want to keep this original data. So how can I go about keeping it? Well, here's a very simple way. I'm going to select this row. I'm going to Control-C to copy it, and then paste it down into the next row. But I want to keep this row the same. Now it's still having all of its basically references activated. So what I'm going to do is, since I still have it selected, I'm going to paste it back into itself using paste special. And I'm going to use values and number formats for how I'm going to paste it back. Now check it out. If I look through, you can see in the function window, these are pretty much all now hard-coded values. And these are, keeping the same formatting, but, they no longer have the function references. They're just previous static data. So now I can pretty much go ahead and use my copying stuff to pretty much change what the next values are for the next version of the bridge. Nice. Alright, so let's go ahead and copy those over. Now let's go to our base reactions first. No, where are you? I'll just do whatever. Okay, joint displacements first, then copy it and paste. Now get your base reactions. Sap base reactions. Paste that in. And hopefully you can kind of see, oh, wait, I'm getting a warning. Uh-oh. So I was saying that my weight has to be listed in pounds, not kips. So I have an auto detection here just to kind of warn me if that happens. And what I'm going to do is going to change my model back into pounds, inches. So this basically workbook output is worthless. Forget about it. Alright, so let's go ahead and display show tables what we really want now. Okay, so go ahead and export this now to Excel, and then we'll do it. Okay, so this is an important check. Always make sure that you're using the right data. So get your base reactions, go ahead and copy it. And there's a lot of room for error here, but I've minimized it by just doing this whole copying and pasting process. So now it should be in pounds. And check it out. Efficiency score is now calculated in pounds. I'm no longer getting any warnings, so that's good. Now let's go back to our overall score history. Open this up and check it out. So here's example 1. We have all our model parameters the same for the economy calculation. So economy score is basically saying the same, but our efficiency score dropped. Why is that? Well, check it out. Basically, lateral deflection dropped minimally, and who cares? It was pretty small to begin with, but our aggregate deflection dropped, which means our aggregate deflection score dropped as well. Our weight went up a little bit, but not by a whole lot, only by maybe a pound or so. So that means our weight score only increased a little bit, which basically means that our overall score decreased. So that's great. And I'll put a little comment here: increased size, tubing size of small webbings in girders to whatever that was, 1/2 inch by 0.035. So it's nice to keep these little comments just to kind of remind you what exactly you did in a previous run. So what's another example of pursuing optimization techniques? Because we've pretty much just tried to change the efficiency, but let's do something to change our economy as well. And what I'm going to do now is I'm going to create a new version. First I got to unlock my model though, and I'll save it as version 0.1.0. So this will be a more drastic change, so I'll denote that by having that higher index change. And what I'm going to do is I'm going to, kind of like the bridge from 2014 that we had, just take out these laterals and just kind of see what happens. Who knows what's going to happen? We shall see. So I'm going to take those out. Go ahead and save that. And now when I run my model, make sure I'm in pounds, inches, and Fahrenheit. just for my output. And when I go to display show tables, get the same output into an Excel table. Now, remember, before we do anything in our original spreadsheet, get rid of the old one here. Before we go ahead and do this, remember we have to copy this down and then paste special with values in normal formats, just so we can lock these values to what they are currently. So now we're using version 1.1.0, and actually we decreased the number of members by 2 because we removed those 2 laterals, so now we're at 55, and the number of bolts we're using is now decreased by 8 technically, because we had 4 per member. So that's a pretty significant drop already. So, assuming that our efficiency doesn't change significantly, then we'll have a pretty decent drop actually in our overall score. So that's a good, this is a good goal. But before we do that, let's go over and kind of copy in our data from SAP, just to make sure that we're not getting excessive deflections now or something. So go into your base reactions. I'm going to copy those over. Oops, no, that's not what I wanted. There we go. Wow, I'm just messing up a lot today. Now let's go back to our joint displacements, get all these, and paste them in. It has to calculate a little bit. Now our auto efficiency scoring has updated, and hopefully our overall scoring will give us some favorable results. Now, it's interesting to note here, and yes, I actually did this lesson beforehand and tested this, and for whatever reason the aggregate deflection is actually calculating to pretty much the same thing. So we're not really affecting our deflection here by a whole lot, or really at all. That's really interesting. We are, however, increasing our lateral deflection slightly, and in fact we've actually decreased our total weight by a decent amount. Of course, we already noticed that we are decreasing our economy score because we're reducing the number of pieces. So this is all very good news. Our aggregate deflection isn't going up at all, and we pretty much just got decreases down the board. So check it out. We've got a really low score. We're almost getting below that 4 mil mark. It's kind of pitiful, but whatever. So I'm just going to do that removed laterals note. And yeah, so that's more or less the iterative design process. You just kind of go through this looping thing where you kind of just change things in your model, or maybe you create a whole new model and then kind of compare results against what you have from previous models, just to kind of compare across designs. And then, just kind of optimize each one individually and then compare the optimized designs for each one. So hopefully that will give you some inspiration for how to pursue optimization techniques, and hopefully we can kind of expand on this a little bit more in future lessons. All right, but otherwise I would say you pretty much got all the tools. So yeah, from here on out it'll be more kind of advanced topics, or kind of just covering certain other things I didn't get to, but now go forth and conquer, I guess. All right, see ya.